Welcome everyone to a video that begins with a mistake I made early in the 2014-15 school year where the topic was units of measurement and ends with me declaring which temperature unit is best. As you may be able to tell from my accent, temperature where I'm from is commonly reported in Fahrenheit. To compare this with Celsius, we looked up the average summer high, roughly 90 degrees, and winter low about 20. These are equivalent to approximately 32 and -7 respectively. A student, familiar with using Fahrenheit for just about everything, asked if the values for Fahrenheit are always greater than those of Celsius. My response was along the lines of, the values we have for Fahrenheit are both greater than that of Celsius, so probably. In modern parlance, I flubbed around, and I'm about to find out because not much time passed before a different student said, apparently -40 Fahrenheit is equal to -40 Celsius. My internal monologue at that moment was something like this.
My God, what have I done?
Ridiculously enough, I knew then as I do now the equations for converting between Fahrenheit and Celsius. So I put -40C into the first equation and got -40, same as it ever was apparently. Then I put -40F into the second equation and got -40 again. I'm 0-2 now, so I begin wondering where that large automobile is to take me home. But I can do one thing that doesn't require me to already know the answer ahead of time, and that is to solve the equations together. I've swapped out the units for y and x because I'm interested in the single value x where the output is the same. The working out looks complicated, but it is fairly straightforward and reveals that the two equations are indeed equal at -40. I was well and truly cooked, deservedly so. I suppose the internet equivalent is to comment on a YouTube video before getting to the end. At least I don't know what that's like. But let's take a closer look at my path to -40. The first two instances were plugging the apparently correct answer into the equations. This is obviously impractical unless I already knew the answer, and if I already knew the answer, why would I even bother? The third attempt was going through the algebra. It was fairly easy here, but would be more difficult with more complex equations. Luckily, there is a fourth and much simpler approach, and that is to just graph the equations. Had I done so on that fateful day, I would have seen very quickly that the two lines intersect at -40. So now that I've realized the obvious benefits that come from graphing equations, it's time to apply it. We all use Fahrenheit or Celsius for day-to-day stuff depending on where we live, but if we want to do some science we may have to leave familiar territory and introduce Kelvin. For my class this usually shows up for the first time with the various gas laws. Luckily it's a rather simple conversion. If I rewrite the equation and solve for Celsius, I can now substitute it in the Fahrenheit equation. I can also do this in the Celsius equation. With these substitutions, I can now convert between Fahrenheit and Kelvin. Since I don't know off the top of my head if there is an equivalence, I can perform the algebra and solve the equations as, just kidding, I'm going to graph them and an equivalence is now obvious. You may have known about -40, but I doubt you knew that Kelvin and Fahrenheit are equivalent at 574.5875. I've shown you two graphs to show two equivalent temperature values, but I don't need two graphs. Let me show you. First, I'll use the equation y equals x to represent Kelvin. Now I can graph the other units with respect to Kelvin. Celsius is easy because it's simply shifted down 273.15, and the two units do not share an equivalence anywhere. I can use the equation for Fahrenheit from earlier and plot it here starting from absolute zero, or -459. As temperature increases, we find the intersection with Celsius at -40. As the Fahrenheit graph moves further along, it runs into Kelvin at 574.5875. For the units we have probably all heard of, this is as far as we can go, so now it's time for the historical and obscure. There are 5 other units to introduce, and first up is the Rankine, which is apparently used in engineering systems where heat computations are done in Fahrenheit. It's an absolute scale based on Fahrenheit. In other words, Rankine is just Fahrenheit moved up 459 units. As we can see, Rankine and Kelvin share an equivalent temperature at 0. Clearly there are no other equivalences, at least physically attainable ones. It does intersect Celsius, but considering it does at approximately -615, we will ignore this and all similar instances moving forward. Next is the Newton, developed by the same Newton you're thinking of. On his scale, he set the freezing point of water at 0 and the boiling point at approximately 33. This is a good time to point out that all equivalences I'm calculating are approximations, and all equations I have used can be found in the description. I calculated that the coldest possible Newton temperature is -90.14. As temperature increases, it first runs into Fahrenheit at -7.18, before hitting Celsius at 0 as expected. There are no physically attainable equivalences with Rankine and Kelvin. Let's move on to the unit which will make my French teacher cringe when I try to pronounce it, the Réaumur. It apparently has use in cheese production in Italy and Switzerland, and I for one don't care what unit they use as long as the cheese tastes good. Once again, we have a unit where the freezing point was set at 0, but the boiling point was set to 80. This information can be used to determine an approximate minimum temperature of minus 218.5. As temperature increases, it first matches with Fahrenheit at approximately minus 25.6. Later, it meets up with both Celsius and Newton at 0, since all three were standardized with the same freezing point. Once again, there are no physically attainable equivalences with Rankine and Kelvin. The penultimate unit is the Rømer. It appears the greatest significance of this unit is that Fahrenheit once visited the Danish scientist and apparently left inspired to create the greatest unit of temperature the world has ever known. The freezing point of water was set at the obvious 7.5, and boiling point at the even more obvious 60. That might sound a little weird, but at least we aren't headed for yet another set of equivalencies at 0. With these standards, I calculated a minimum temperature of approximately minus 136. First, Rømer meets Newton at minus 12.7, before finding Fahrenheit at minus 2.5. Later, the scale runs into Celsius at 15.7, and finally, Réaumur at 21.8. Rankine and Kelvin are probably feeling left out of all the fun right about now. My exhaustive research into temperature scales involved only the Wikipedia page, which means there is one unit remaining, the Delisle. This unit sets the freezing point of water at 150. Okay, that's a bit weird, but the freezing point of water is 273.15 Kelvin and nearly 500 Rankine, so nothing truly out of the ordinary. Delisle then sets the boiling point of water at the very sensible 0. Yes, 0. Nevertheless, we have enough information to add Delisle to our graph, and this unique unit has a minimum temperature value of approximately positive 559. We find Delisle equivalent to Rankine at 305, Kelvin at 223, Fahrenheit at 96, Celsius at 60, Réaumur at 52, Rømer at 44, and finally Newton at 27. That's right, the only temperature unit that has not only mathematical, but physically attainable equivalents to all other units is the Delisle. With all of this information about the modern and historical units of temperature, I feel it is only right to deliver a verdict on which one is the best, especially since no one asked for it. My first consideration is whether the unit fits our perception of temperature, which I would imagine for most of us means that what we feel as hot registers a higher value. Unfortunately, this means the Delisle, despite its connection to all other units, must be dropped from consideration. All remaining scales fit our perception, so the best of them should be the one that has the most physically attainable equivalences with the other remaining units. It's easy to see for some, but really tough with that mess in the middle, so here's a clean version. The absolute worst scale for equivalences is the Rankine, which only matches one of the other 6. Kelvin does slightly better, as it also matches Fahrenheit, but it's not the best either. Following is a 4-way tie for second with Celsius, Newton, Réaumur, and Rømer, all matching with 4 of the 6, with the exceptions being Kelvin and Rankine. That means the undisputed champion of temperature units, matching all but Rankine, is Fahrenheit. So here I am, over 10 years after making a silly mistake, making even sillier conclusions about temperature scales. Had I not made this one, I probably would not remember the significance of minus 40 like I do now. Additionally, I almost certainly would have never discovered 574 for myself. I also never would have even bothered reading about historical temperature scales and finding that the Delisle, despite its ridiculous nature, is the only temperature unit compatible with all the others. Just as you will now never forget that Fahrenheit is the superior temperature unit, don't worry, I also couldn't do anything to forget the mistake I made in class. While the students in that class have probably long forgotten, they didn't let me forget it, as the very next day I found this posted in my classroom, where it remains to this day. This seems like a perfect time to thank you for watching this video before something else can possibly go wrong.